try to get through this. We went over number 5 in class today. Talked about that this cross product R only really tells us the angle this thing is going. So as you get closer to this spot, this angle gets larger. So you approach the sine of 90 degrees, which approaches the maximum amount. So that cross product R hat is not anything plugging in that distance. It is just a direction. For number 14, it was asking for the field strength at A, B, and C. So in this particular case, we need to find the field from each wire at those positions. So with the current going the top wire to the right, at point A, the field is coming out of the page. The current going to the left in the bottom wire, that field would be going into the page at A, but it'd be much weaker because that wire is 6 centimeters away instead of 2 centimeters away. So when the fields are going opposite directions, we're going to subtract them to get the net field. In the middle here, if you notice, the field at point B is going into the page caused by the top wire and also into the page caused by the bottom wire. So we would add those two fields together. So the key thing is since the distances from the points to the wires are either 2 centimeters or 6 centimeters, that's the only things I really need to figure out in terms of the math. So from the top wire, I end up with 1 times 10 to the negative 4 Tesla. Bottom wire, the field is 0.00033 Tesla, or 3.3 times 10 to the negative 5th Tesla into the page. That's at point A. Point B, so the net field there is 6.67 times 10 to the negative 5th Tesla out of the page because the field is stronger caused by the top wire. At point B, each wire contributes this 1 times 10 to the negative 5th Tesla. So it should be 1 times 10 to the negative 4th Tesla. Gosh, I am having issues. So I'm going to do this. Here I'm going to do this. This. So that is negative 4 Tesla. Okay. I don't know what. No, I'm an idiot. Never mind. So this is 2 times 10 to the negative 4th. The bottom, it's the same thing as point A. So we end up getting a net field of 6.67 times 10 to the negative 5th Tesla out of the page. For P21, since this is going clockwise loop, we would think of the curvy hand rule. Our fingers point into the page. So that says the positive direction is into the page. So I've got 2 amps into the page, 6 amps out of the page, an unknown number of amps here. If we use Ampere's law, we said that this would equal this number of Tesla meters. That's our constant multiplied by the net current. The net current actually is going to end up being 3 amps, and that means that I3 is 7 amps into the page. For problem 33, this is a wire that's held. So this is similar to the example I did in class on Monday the 17th. Here we have a gravitational force down, but a magnetic force up. So we're trying to find the field strength and direction that would levitate the wire. So I'm going to use my flat hand rule, and the palm of my hand would point up, which is the direction of the magnetic force. The current is pointed to the right. So that means that the field would actually come out of the page. So that's my attempt at drawing dots. Big idea here, balance forces. Let us figure this out. So the magnetic force would be equal to B times I times the length of the wire. Gravitational force is mg. That gets me 0.131 Tesla, again, directed out of the page. For number 34 here, I've got a current that's going clockwise. It's in this particular field. This is a 0.10 meter direction cross section of the wire. Current's going down based on this. We know it's 5 amps of currents based on Ohm's law. So with the downward current in the field shown, the force has to be to the right. It's 0.025 newtons. Here, this is similar to the earlier problem where we ended up having 3 parts to it. So it's similar to problem 14. And I screwed it up here, trying to write things off because my distances were weird. So I think I was thinking about the earlier problem where the distances were 2 centimeters and 4 centimeters, or 6 centimeters. Here it's 2 and 4 centimeters. So again, I can think about the force between these. I use BIL, but B is equal to this mu OI over 2 pi R. So putting those two together, I get this formula for the force between two wires. So but at a 2 centimeter distance, we get this force. At a 4 centimeter distance, we get half the force. So what I can do here is I can realize that the top two wires repel, but the middle and the top wire repel, the middle and the bottom wire repel. That gives me no net force on the middle wire. Looking at the top wire and the bottom wire, then we can see the force on those and compare that the force on the top and the middle wire. So the top wire is repelled up from the middle wire, but is attracted down to the bottom wire. So it's a net force that's going to be up on the top wire. And again, I screwed the numbers up here because I screwed this distance up. So we're going to see symmetry here like we did in problem 14. No force on the middle wire, force up on the top, force down on the bottom. The numbers are this. The announcements are going to come on, so I'm probably going to stop in just a moment. So that's the net force. We did number 50 in class. And for 60, I'm going to show this. If you have any questions, let me know. Again, I've screwed up a lot with this, but notice here we're having the electric and magnetic forces being equal. The charge actually cancels out. This is important for understanding how to get electric field strength, though. Left-hand rule for an electron, that's what I screwed up about initially, because I had my fields or my forces reversed, and therefore I had my direction reversed. Okay, that's it. Thanks.